Alright, this is a demonstration on how to use the PVC permeameter to calculate hydraulic conductivity. The first step we're going to do is disassemble the system and separate the soil chamber from the outlets. I'm going to measure the radius of the internal radius. In this case, approximately 7.5 centimeters. And we're going to measure the total height of the chamber. In this case, about 15.5 centimeters. We're then going to take the chamber and fill it with our preferred soil. In this case, I'm going to be using a fine sand, uniform sand, and we're going to measure the length of that sand. It's recommended that we use about a minimum of 2 inches, and then the system is approximately 6 inches tall, so we can fill to 6 inches. In this case, I have filled approximately I have about 9 centimeters of space remaining, or 6 centimeters of soil. So the length of our soil will be 6 centimeters for this example. Next, we want to reassemble the system. The outlet can be placed on top, and then the chamber with the outlet is returned to the system. Any location where we can disassemble the permeameter, we need to apply a putty. You should have access to plumber's putty, and we're going to apply it as a temporary sealant. Once putty has been applied to both ends of the chamber core, we're going to move on to filling the system and checking for leaks. Begin filling the system. Begin filling the system from the left side. This will saturate the soil from the bottom up. And again, we're going to check for any leaks anywhere we applied putty. Next up, we're going to determine the hydraulic head that's going to be applied on the system. We need to measure from the ridge where the break point is for the outflow to the top of the system. On this particular system, it's measured at 16.3 centimeters. We're then going to take our water bottle that applies the constant head and determine from the spot where it rests to the end of the straw, and the end of the straw indicates the beginning of the water column. In this case, from the line I marked to the end of the rubber stopper is 3.5 centimeters, and then an additional 6 centimeters. We then take the 16.3 centimeters and subtract the 9.5 centimeters, and that is the head that will be applied to the system. Typically, we want to overflow the system to allow water to begin flowing out, and then we're going to apply the water bottle and allow the system to reach a steady state of flow, typically indicated by the bubbling of the water. And we can watch our flow and see that it is fairly consistent. Now that we have steady state flow, we're going to want to time how long it takes to fill a beaker. In this case, I have a 250 ml beaker, and I'm going to fill it to 200 mils. In this case, it took 20.37 seconds to fill the system, to require 200 mils of water. At this point, we have almost everything we need to make an example calculation. We have our diameter, we want the radius. So our radius will be 3.75 centimeters. And we can use that to find the area, which will equal approximately 44.18 centimeters squared. We need for Darcy's equation, we'll need Q, which is our volume over time. So in this case, we have 200 over 20.37. And we're going to take milliliters and use that as centimeters cubed for 9.82 centimeters cubed per second. Following Darcy's law, we have now 9.82 centimeters cubed per second, which will be equal to our negative K times our delta H of 16.3 minus 9.5, or 6.8 centimeters, over our length of 6 centimeters, and then times our area. Now I have everything we need to calculate conductivity in centimeters per second. The right side of the equation will simplify down to negative K times approximately 50.07 centimeters cubed. That's in centimeters cubed. And when we solve for K, we get a negative K equaling 0.196 centimeters per second. We can convert that into meters per day if we want for an easier to look at or possibly understand form. In that case, we will divide by 100, multiply by 60, multiply by 60, and multiply by 24 to get a hydraulic conductivity of 169.45 meters per day.